Hi, I'm Judy Cole, the Executive Vice President and CEO of the MIT Alumni Association, and I'm delighted to welcome you to this web production of the MIT Alumni Association.
Okay, welcome to the MIT Faculty Forum Alumni Edition. I'm Dan Falk, science journalist and former Knight Science Fellow at MIT. This is an interactive forum, so we encourage your questions. Use the Google form below the live stream to ask a question, or tweet your question to hashtag MIT Better World. We'll get to as many of your questions as we can. This month, we delve into the future of quantum computing, a very interesting topic and one that's been in the news quite a lot in recent years. And we'll look at how quantum computers will change our lives. Does the first quantum computer already exist? And if not, when might we expect to have one? And how can we know if a computer is, in fact, a quantum computer? Our guests will share some of their research on quantum information and probably on quantum physics more generally with us, and they'll address these and other questions in today's forum. So I'm just going to briefly mention our three panelists, and then they'll introduce themselves in a bit more detail. We have Stephen Jordan from National Institute of Standards and Technology. We have Ramis Movassagh from the T.J. Watson Research Center of IBM. And we have Dmitry Pushin, a professor at the University of Waterloo in Ontario. So to begin with, I'll have each of you just, again, to reiterate who you are and just to give a little 2-minute blurb about the kind of research that you do. And I think we decided that Stephen was going to go first, so take it away.
Sure. So my name is Stephen Jordan. I work at the National Institute of Standards and Technology in Maryland, also at the University of Maryland, which is where I am at the moment. And I did my PhD with Eddie Farhi at MIT in 2008 in theoretical physics. And what I worked on then, which is also what I work on now, is basically quantum algorithms and quantum computational complexity. So the quantum algorithm side of things, the essential question is, suppose we do have a large-scale working quantum computer, what would it be good for? What are the things that we can do with it that we couldn't do with conventional computers? The complexity side is a little bit more broad. It has to do with what's the computational power of different systems, and as the aspect of that I usually study is different physical systems. So if we have something that might not quite be a quantum computer, maybe it is at a high temperature, it's not in a tightly controlled state, might we still be able to compute some things with it that we couldn't with classical computers? Or maybe if we had some more exotic system involving relativistic physics, could that compute things that ordinary quantum computers cannot? So basically comparing the computational power of different systems.
Okay, thank you. And Ramis, do you want to go ahead?
Sure. I'm Ramis Movassagh. I'm currently at IBM T.J. Watson Research Center in Yorktown Heights. I did my undergraduate in applied physics at Cornell. Then I spent some time in Switzerland doing neuroscience and mathematical physics. Then, like Stephen, I did my PhD at MIT. I was in the math department, and I worked with Peter Shor, whose factoring algorithm you might have heard of. And so my research interests are applied math and mathematical tools applied to physical sciences, including, say, chemistry. So in the quantum information aspect of my work, I'm mostly interested in quantum many-body systems. So what are the questions you ask are, how can we describe and simulate or predict the behavior of many interacting quantum particles? Now, everything in the world is quantum because we're made up of atoms and electrons, etc. But the mechanics and the laws of physics that we require for everyday objects, like a pen, being thrown into the air or what have you, the classical laws that we have are sufficient. But if you have atoms, electrons that are interacting, then the laws that apply to describe their physics and their behavior is described by quantum mechanics and quantum physics. And there is some inherent difficulties in simulating quantum many-body systems. So it turns out that the amount of work and resources you need are exponential. They grow exponentially with the number of particles, whereas, for ordinary matter, you're looking at something that scales linearly. So just to be able to describe and simulate quantum many-body systems is a very daunting task. So then the question is, can you give an effective description, some effective theory, some reduction in the number of parameters that would allow you to, with high accuracy, predict the behavior of these many-body systems. Now, some particular incidences that I've worked on are disordered systems. These are, where the interactions have randomness in them, and a big part of my work is in applying mathematical tools, say from random matrix theory, numerical linear algebra, operator theory, to better understand the properties of these quantum many-body systems.
Okay, thanks. And Dmitry, why don't you take it away?
Hi, so my name is Dmitry Pushin, and I received my, undergrad degree, bachelor degree in Russia, in Moscow Institute of Physics and Technology, where I kind of studied condensed matter, specifically high DC superconductivity. I also spent some time in Switzerland studying magnetism, so I'm experimentalist, just to say. And I finished my PhD at MIT with Professor David Corey, and I was studying really coherent control of how we can manipulate a quantum particle such as a neutron. And why neutron? Neutrons is the most common building blocks of matter. It's also a unique probe for studying materials and fundamental interactions. It's the only electrically neutron nucleus. The neutron passes through most of material with ease, even at the lowest neutron energies. Nowadays, neutrons, even with a lifetime of about 15 minutes, you can tell yourself if it's a long time or short time, are used to study problems ranging from a discharge of the common batteries and to cosmological dark energy. And my research is focused on a neutron as a quantum particle that exhibit coherence. So the ultimate manifestation of coherence is interference, and the ultimate measurement of interference is interferometric. So in my group, we use neutron interferometers. One example is Mach-Zehnder interferometer, to fork neutron into superposition states, which are separated by decimeters, to explore microscopic quantum interference. And some of the recent examples which we studied there, it includes search for the dark energy, using quantum information concepts to enhance the device itself. So we actually built first kind of neutron interferometer based on the quantum information, which is insensitive to specific kind of nodes. We employ decoherence-free subspace, and we also try to explore different degrees of freedom of the single particle. So we kind of studying of neutron, which can have several different paths it takes. Neutron also has a magnetic moment, so it's a small, it has a spin. So we can use that degree of freedom. It also could be set it in a different energy levels, where people use different energy levels to add additional degree of freedom. So having one particles with many degrees of freedom, you can think of single particle entanglement, where you can study with a single particle of several qubit systems.
Okay, thanks, Dmitry. And why don't we go back to Stephen, and if you could just give us a sort of a 2 to 3 minute overview of why people are excited about quantum computation, and how it's different from classical computation. I appreciate that perhaps for some people in our audience this is old news, but on the other hand, we may have some folks who really aren't too familiar with these ideas. So just give us a little introduction to the field and what the promise is, why people are excited about it.
Sure. Well, people have been thinking about computation for a long time. Even back in the 30s, people like Turing and Gödel and Alonzo Church were formulating mathematical definitions to try to understand what is computation, what's not computation, what can computers do, what can they not do. And in the subsequent decades, a consensus emerged that the set of problems that you could solve with computers was very much insensitive to the details of what the computer was, whether it was built out of silicon or built out of Tinker Toys. And really no exception was found to that for many years, up until sort of a bombshell arrived, which was the idea of quantum computation. It was the first challenge to this notion that all computers are basically equivalent. They can all do the same set of things. One might run twice as fast or even 1,000 times as fast as another one, but which problems can you solve in polynomial time, and which are the problems that are just totally intractable that take exponential time to solve? That dividing line seemed to be independent of how you built your computer. But quantum computers are so far the only real challenge to this idea. And so that's one reason, sort of a theorist's reason, why people are excited about it. Now there's also a more practical reason to be excited about quantum computers, which is the list of specific things that they apparently should be able to do exponentially faster than classical computers. The most famous of these is the one that was discovered by Ramis's advisor, who's now at MIT, Peter Shor, which is factoring integers. So if you have an integer that's n bits long, the best classical algorithm for solving this requires time that scales as 2 to the n to the 1/3, roughly. So it's almost an exponential time algorithm. Beyond about I don't know, 500 or 1,000 bits, you just can't do it, even with the biggest supercomputer in the world spending millions of dollars on CPU hours and stuff. Whereas a quantum computer can solve this problem in time which scales like the cube of the number of bits. And so that's a huge difference. So for example, I once ran the numbers and computed what's the largest integer that you could factor if you took all of the silicon in Earth's crust and converted it into like present-day CPUs, 2 gigahertz type things, ran it for the age of the universe, and made optimistic assumptions about how parallelizable this problem was. And that was about 5,000 bits. And if you had a single quantum processor that ran at 1 gigahertz intrinsic clock speed, factoring that number would take you like 2.5 hours. So you know, it's a really dramatic thing if you plug in actual numbers there, which people usually don't. So you might ask, so why do you care about factoring integers? So one class of people who care about that is cryptographers, because they can break codes. But from a more fundamental computer science point of view, it just points to the fact that here are these exotic new machines which can do things that are way beyond the reach of ordinary computers, which no one was expecting to ever find any machine like that. People really thought that all computers were equivalent in terms of what they could solve in polynomial time. And then so the big question became, all right, number one, how do we build these things? And number two, what else might they be able to do? Maybe the most compelling other example besides factoring is simulating other physical systems, predicting the outcomes of chemical reactions, et cetera, et cetera.
Okay, thanks very much for that introduction, and I think we can see where, you know, the promise of quantum computation could sort of lead in many different directions, right from the get-go. And of course, we can also point out that this field is sort of in its infancy, whereas classical computers have been around for, well, 75 years. Maybe I might be off by a few years, but this field is just getting started. I want to go to Dmitry now, who is the experimentalist of our group. And Dmitry, can you say a few words about how you take this from, you know, theory, this very clever idea that we've had for a little while, and actually implementing it? For example, with classical computers, you know, we went through this phase, all right, we'll try vacuum tubes, and then we'll try transistors, and things sort of evolve. But I understand with quantum computation, it's kind of like, you know, a struggle even to figure out what a qubit ought to be. What should they be? How do you connect them to each other? So can you talk, Dmitry, about, you know, the struggle of actually building one of these things?
Yeah, so if you think of normal computers, what we have, again, it's a silicon, and most of them are based on just simple transistors, where we either have a signal or not have a signal, so it's basically bits 1 and 0, and any calculations you do is, of course, any transistor will have a charge or not, so we use the electric field to control these devices. And still, we're trying to reduce these devices to go faster and faster, and eventually, nowadays, I guess, what's with tens of nanometers, it's really harness of the few, I don't know, few thousands, few 100,000, maybe millions of the atoms themselves in a single transistors. So let's remember that in the atomic space in all the silicon devices, it's in the order of few angstroms, so it's in the order of nanometers or less. So if we try to reduce these devices to make them smaller and smaller, the quantum mechanics kicks in, and we have to kind of think of transistors a little bit different. Even though nowadays the transistors are kind of small, we still not use their inherited quantum properties. Like, for example, in a silicon, that would be the spin of the electron. And if we will harness the spin of electron, of course, there will be some gain maybe in using less energy, and of course it could be also faster. And again, in this case, what's quantum bit will be, it's a superposition state of the spin. It's either in the up state or down. In case, for example, in the neutron interferometer, I send neutron in two paths, so it can take a two path. It's again like I can control it if it's going to be spending more time in one path or another, and that I can introduce some phase shift. So this is kind of basic idea of what a quantum bit would be. So instead of having 1 and 0, you have a superposition, and that's kind of inherited properties of quantum mechanics. So you can have a superposition of at least in one qubit. If you have several qubits which are coherent, you can have a superposition of many qubit states. And that was one of the explanation, I guess, by Stephen to say, like, we can really just having a few atoms, we can increase the power of computation or storing the memory. Again, with having like 50 or 60 atoms, we can have a memory which is comparable to whatever all the memory of the universe we can build on now. And if we have like maybe a few hundred qubits using like few hundred atoms, where we can either use the spin states or some energy states, we can build much more powerful computers. And of course, there are different systems. Some of the systems which nowadays considered to be very prominent is the ion traps, and recently there was publication in Nature where actually people use a few ion traps to build a universal kind of quantum computer or programmable quantum computer. That you can program not just a single algorithms, which was possible only before you really build a quantum computer which can solve specific algorithm problem, but people show that they can program this quantum computer on a 5 bits that they can see what the inherent problems could be in the future if you want to really try to coherently control the whole devices. There was also big advances in a squid-based quantum computers where they use the current kind of degree of freedom, when we have either current which goes from left to right or from right to left, that would be inherited qubit. On using the small schemes, people try to use the quantum dots, try to use atom floating on the surfaces. Again, I'm trying to use neutron as a quantum device. Maybe it's some of the ideas not really, like, at least for now, it's not clearly how you can expand them. But still, there could be some properties, not only just building quantum computer itself, but also like creating a new devices which will be much more robust against the noise and much more sensitive. So you can study forces of nature which wouldn't be available to do before.
Thanks for that, Dmitry. And just a quick follow-up. Tell us what the current state of the art is. I mean, for example, number of qubits. Like, where are we at the moment? Do we have something today that we can point to and say, yes, this is a quantum computer and we've used it to solve such and such problem? Dmitry, where do we stand at the moment?
So there is few, of course, debatable questions, but let's say what most people believe, that we have at least like 15 qubits systems maybe a bit more, maybe a bit less, which are fully controllable, which you can have a nearest neighbor interaction, so you can control the phases of each, either it would be the squid or the ion or some other properties atoms.
Okay, thanks. And we've got some questions that are already coming in online, but just before I go to them, I'll ask Stephen and Ramis, did you want to pick up on anything that Dmitry has been saying there, or do any of you have a question for each other before we go to our audience questions? I don't.
Well, I might add one more comment, which is that so a metric that gets talked a lot about, I think, especially in the press, is number of qubits. And there's also another metric which I think is important, maybe even more important, which is basically the precision, the coherence times, and that there's been a lot of progress over the last few years about making the qubits last longer and be more resilient against errors. And I think this is going to be one of the key things going forward in scaling up quantum computers, and that's a thing to really pay attention to. In particular, there's a threshold which says that once you get your error per operation down below a certain level, maybe 0.1% or something, then in principle you can use active error correction to correct errors as you go along and then perform arbitrarily long quantum computations. And so that's like, I would say, a very significant milestone. In theory, people have now demonstrated, say, single qubits or 2 qubits very carefully isolated that nominally are below these fault tolerance thresholds. It's not quite the finish line yet, because you need to be well below these thresholds, otherwise the size of the error-correcting codes you need to use is just too large and not practical. But I think that was a key milestone anyway, that was one of the things that triggered this recent wave of interest from industry giants like Microsoft and Google.
Okay, thanks. And I'm just looking at our questions that are coming in online, and we've got a fair number already. Some are what I would say are quite technical, and some are a little more layperson-oriented. So with my own bias towards things that I myself can sort of understand, I'm going to take a question from the audience that is fairly straightforward. And the question is, how do you think quantum computers could aid NASA in designing or executing space missions? So would one of you like to address that question? Or if not, we can go to another question. But
I mean, we can think of the exchange of information. Sometimes you need to encrypt something. This is going to be, for example, encryption key transfer, and these technologies already exist. People try to actually communicate with the satellites using quantum information for the cryptography or the information exchange. And of course, like maybe NASA trying to talk about some devices which they need to measure. I don't know, like. There's a lot of ideas try to put some quantum devices on a space station and do a lot of measurements, even for the fundamental physics. To study gravity, we really need to know, for example, big G to the quite high precision, to 10 to the minus 6 level, to really kind of understand better world.
And there's another question quite related to that first one, which is, can you comment on the Chinese quantum communication satellite? I know this was in the news recently. Dmitry, can you say a word or two about that? Or
maybe I'll pass.
Oh, okay. All right, let's go to the next.
Well, I mean, so the what they're demonstrating, I think, is quantum key distribution. It's a way of transmitting data that cannot be eavesdropped upon. The usual way of doing this is over fiber optics, but it's limited in its range to maybe a couple of 100 kilometers. A different way is to transmit the photons through free space using telescopes, basically, and bouncing the signals off of satellites. And in principle, this might be able to achieve somewhat longer range than the fiber-based systems. It's pretty expensive, though.
Yeah.
Okay.
I mean, it's a
Thanks.
health
I'm going to go to another question that that is, I think, fairly answerable. I think, or at least should be easy to have an opinion about it. The person asking the question. Oh, sorry. I thought I should maybe credit someone named John C. And sorry for not crediting the first two questioners. John says, I'd love to hear a quick answer from each. Will government, academia, or industry drive the most innovation in this field? So government, academia, or industry? Where do you think the innovations are going to be coming from?
Well, I could say maybe a couple of words.
Please.
So right now, everybody is active on it. Certainly universities. As you can see, one of our panelists is working in a university. And Stephen is at the National Institute, and I am at a private company, IBM. So there certainly are, there's quite a bit of activity in various sectors. However, in the industry right now, there seems to be a good push from companies that have quite a bit of resources. So Google, IBM certainly recently launched this some of the cleanest qubits. So there's a lot of push. Government, from what we know, has a good push, but maybe Stephen can say more. And they may be doing more things that we don't know about. And certainly there are a lot of both theoretical and experimental activity at universities. Some universities have embraced quantum information and computation more than others. So in academia, it's not. It's a very interdisciplinary field, so it doesn't have a natural home. You cannot necessarily place it exactly in mathematics, physics, or computer science. It's a little bit of all. So it's had a harder time, at least for theorists. I guess experimentalists, they would have a natural home in physics or perhaps maybe electrical engineering. But as far as theorists are concerned, not every institution has embraced quantum information as well, but it's certainly picking up, and we see more and more hires and initiatives from the academia as well.
Did any of the other two panelists want to weigh in?
I can add something. Maybe we'll quote Ray LaFlamme on a saying like, it's really our curiosity of understand the world pretty much driving us to study a lot of new phenomena. We live in an era of, I guess I would say, a new revolution of the quantum control. So we understood quantum mechanics, and now we try to harness it, to use it in a everyday's life. And maybe that would be quantum computers, maybe it would be just quantum sensor. And that could be like some way of program of, I don't know, some maybe combining some molecules, designing new drugs. And I mean, you can see there is a conglomerates already. There are universities merging with some national labs, like Joint Quantum Institute. It's a national lab and university try to build specifically based on a kind of quantum information, quantum mechanics, bringing people together to study that. There is, of course, a lot of interest in the government, let's say maybe military, and of course in academia too, because again, maybe we're curious.
Thanks. And before I'll go back to the audience questions in a moment, I want to just, there's a famous quote from, you guys, this will sound familiar to you guys, but back in 1943, the chairman of IBM, actually, I should fact check this quote because maybe it's, he said only 5 people in the world are going to need a computer. Now, of course, it turned out that a lot more than 5 people need a computer. What can we say at this stage? And I know it's tricky because quantum information, quantum computing is in its infancy, but are we talking about something that, everybody is ultimately, all our lives are going to be affected by? Or are we talking about sort of niche applications, and for the most part, regular folks can just get by with classical computing the way we've been doing up until now? Whichever one of you might like to have a thought on that.
I think at the very advanced stage, if one day we do have a quantum computer and it's fairly powerful, it will affect our lives in so many different ways that everybody will be either directly or indirectly affected by it. To give you, one simple example, right now, somebody spoke of NASA, so people have very little trouble sending spaceships to distant places using various slingshots or having a little probe sit on a comet of, with a length scale 2-kilometer rock, basically in empty space. So this takes a lot of control, understanding, and a lot of accuracy in simulating these classical systems. But once it comes to quantum matter, even to simulate, like 100 spins or 200 spins, takes a tremendous amount of resources, and we can't really do it exactly. But if one day we do have a quantum computer, we can do that very naturally, and that has various ramifications. One of which is that we understand quantum matter better, and understanding quantum matter better would, in principle, can revolutionize not only our electronics, but perhaps biology and chemistry, certainly chemistry, and so its impact on our lives is going to be tremendous. Now, whether there is a particular use for a quantum laptop that everybody should have, so there's certainly search algorithms that are faster. There is Dima mentioned. There is also communication that they can do faster using quantum computers. But the field of quantum algorithms and coming up with uses for quantum computers is very much active and alive. So it could very well be that we have new. It's actually a difficult field. Coming up with useful algorithms is very hard, but it's not out of the question that we'll have more and more uses for a quantum computer, and that could change the usability of it and the widespread usability of it.
Yeah,
Okay.
just one thing I might add is that I think it's useful to keep two distinct questions. One is whether quantum computers will be something that we'll have on our desk or carry in our pockets or whatever, something that we'll physically possess, versus whether it's something that we'll use on a day-to-day basis over the cloud. So like, the Google cluster, it's not something we carry around, and it's really quite different from the computers that we have on our desk in some sense, although not as different as a quantum computer. But it's something that we access every day and interact with every day, and so I could see quantum computers being like that, even if we don't really have them physically with us.
Okay, thanks for that. I know, again, this is it's tricky. That quote, Yogi Berra said, predictions are difficult, especially about the future. And I know this is a little bit tricky, trying to imagine the future of a field that's just beginning. I'm going to go back to our audience questions, and it's just a fairly straightforward question about the state of the art of quantum computers from Larry Smith in Austin, Texas. And he's asking, when do you think we will have a quantum computer that can factor an integer faster than a PC? All right, so that seems like a fairly straightforward question. Can one of you, by the way, has it already been done? If it has, please tell us.
My guess is not at least until the 2030s.
I think there is a few programs which really are kind of funding the ideas of building a quantum computers with 100 bits, and like I think IBM is one part of it. There's a few projects try to do something like that, and would it be like 10 years project or 20 maybe?
And also, you probably know, so I'm talking to the person who asked the question, so factoring has been done for small integers like 15 or 21. So we do have quantum computers that you drop a lot of money on, and they can factorize 21 to 3 times 7 probabilistically.
Thank goodness.
So that is nice because, we do have proof of a principle, but so I think the person actually articulated the question well to say that, can we factor a number at least as fast as a classical computer? So one is the speed, of course, the cost going into it, and second is that, does the probabilistic answers you get from a quantum computer, so that's a negative thing, right, compared to a classical computer. But at some point, if you can do it large enough that it outweighs the fact that you get probabilistic answers, is yet another thing that should be weighted into the
Ramis, I just wanted just to clarify for listeners who may not be familiar with this idea, when you say a probabilistic answer, this is when the computer does the computation, but then says, oh, I might be wrong, here's the probability that I'm right. Is that what we mean by this?
Right. So you basically, the key difference between quantum mechanics and classical physics is that the laws of quantum mechanics are not deterministic. So at best, you can predict the probabilities with certainty. You cannot predict a particular outcome with certainty, but the probabilities with certainty. And the quantum circuits that you give an input into a superposition. That superposition is a statement about that probabilistic nature. Then you put a circuit that implements the algorithm. Then it gives you an answer, and the answer is based on interference. I think it was mentioned earlier. So the interference will say, well, with a high probability, you'll get what you want if you have a good algorithm or experimentally a good circuit. And with a low probability, you'll get garbage. Now, at every given instance that you run the algorithm, well, you might get garbage, but with lower probability. But the good thing is that the useful quantum algorithms are just so much faster that compared to the classical simulation, even if you get garbage, it's fine because you can run it 10,000 times on the same task. You can run it 100,000 times on the same task. It'll take less time, much less time than your classical computer, and you can easily tell that with the probability that you expect, for example, say even two-thirds of the time you get a particular answer, so that must be the right answer. So the answers are probabilistic, but for good algorithms, they're outweighed by the fact that the algorithm runs very fast. So then you can decisively tell.
One thing I would add is that I expect that factoring will not be the first thing that quantum computers outperform classical computers at. What I think will happen first is we'll see quantum computers outperform classical computers at some kind of made-up problem that nobody intrinsically cares about, but which is just kind of cherry-picked to be easy for quantum computers and hard for classical computers, and this will be done as kind of a demonstration. People refer to this as a quantum supremacy demonstration. And I think that will be first. I think that will actually is likely to happen even within the next 5 years. I think the next thing that will happen after that is maybe quantum computers outperforming classical computers at some kind of simulation task relating to chemistry or material science. And then outperforming classical computers at factoring will happen a number of years after that, because as far as we can tell, it takes a fairly large quantum computer to run these factoring algorithms.
We're down to about 6 or 7 minutes, and I want to try to squeeze in another audience question, but there's also something that I want to ask the panelists, just because it has been in the press a lot. As you folks know, there's a Canadian company called D-Wave that allegedly has built a 512 qubit computer, and they've actually sold quantum computers to NASA and to Lockheed Martin, and according to Time magazine, they sold one to a U.S. intelligence agency, but the magazine wouldn't say which agency it was that bought the computer. So 512 qubits, wow, that sounds like a lot. Can one of you comment, do we know what sort of a machine has D-Wave actually built? They've obviously built something. Is it a quantum computer?
Well, it's a special purpose device. It's not the kind of quantum computer that could ever do factoring, for example, or even necessarily simulation. It's really a special purpose device just for optimization problems. And it's not exactly a digital machine. It's sort of more like an analog machine. And I think D-Wave has demonstrated fairly convincingly that this machine does solve optimization problems. There's much debate about how quantum it really is, and other debates about how scalable it is, how useful it is, etc. But I'd say the basic point is it's intended to be kind of a special purpose quantum computer. Oh, I lost your audio.
Yeah,
no,
lost
that's
your
my
audio,
fault.
Dan.
That's my fault.
Oh.
I muted my microphone and forgot to unmute it, but that's okay. I wasn't saying anything important. I'll try to just squeeze in this last question from, again, this person is in Austin, Texas, so I guess they like us in Texas. It's Mikhail from Austin, who says that he's worked on fusion, which is another field that's has a lot of promise, but is also sort of in a certain sense struggling. And he says that it was always difficult securing funding, and he wants to know what the funding landscape is like in the research that you people are doing. Is it you just send out the grant applications and the money comes in, or is it a bit of a struggle? Tell us how much confidence there is in the work you're doing from the people who actually fund it.
My sense is that it's we have it better than a lot of other neighboring fields right now.
Yeah, I think so too. I mean, there is a lot of big push on quantum devices, quantum materials, and which also involve the quantum computation. There is still funding, and people. I mean, okay, let's say this way: I didn't really apply for many funds. Just in my particular research, because I was trying to really build a specific device, but I know people get funds, and the funding is not bad.
Oh, okay. I'll turn to, I think we're getting close to the end here, but let me just try to take this last question from Jessica Lamb, who graduated from MIT in 2008, and she wants to know, sorry, I have to lean forward to read the small print here, but how can artificial intelligence and machine learning help increase the development of quantum computers, e.g. increase precision of time or coherence of atoms, and are there currently places working on this? So in other words, I guess, AI, which is another field that has been in the news a lot, can AI help in some respect with the work that you people are doing?
So there has been some discussion about optimizing architecture of quantum computers using machine learning tasks, where the circuitry or the wiring, which I'm not so familiar with, but an experimentalist would be, perhaps could benefit from machine learning. Now, maybe other people can comment more about. There's certainly been some activity about quantum machine learning and quantum artificial intelligence, but that's a different angle than Jessica's question.
Maybe I can comment in a sense, we trying to do the quantum machine learning to search for the different algorithms. One of the major problems, and I guess one of the leading part, is to really have a coherent control. And if we scale to many qubits, it's, of course, you will need to have more options, more devices, I don't know, better control environment, because you still scale control. And I mean, with a quantum machine learning, in case we come with ideas how to do the better control of quantum system, if it would be useful, of course, it will be applicable.
Okay, Dmitry, thanks. And at this point, I will wrap things up. So a big thank you to Dmitry, to Stephen, and to Ramis, and to our audience following this online. On behalf of the Alumni Association, thank you for tuning in to this Faculty Forum Online Alumni Edition. Thanks again to our alumni panelists from Waterloo, from NIST, and from IBM. We didn't get to all the questions submitted, but rest assured that our panelists will see them all. You can tweet about today's chat using the hashtag MITBetterWorld, and send follow-up questions or feedback to alumnilearn@mit.edu. Thanks again for watching. Thanks, everybody.
Thanks again for joining us. For more information on future MIT Alumni Association productions, please visit our website.